Hello everyone, and welcome to another C++ template metaprogramming video. In this video I'm going to show you explain to you as well what universal references are. And before I am going to explain you that or show examples of it, I am going to write some rules first in order for it to be a universal reference. So, the first rule is that it has to be a function. It has to be the template class, or the template parameter has to be part of the function signature. So let's say, let's just say template class. Or let's just say the template parameter must be deducible. And by deducible, I mean that the compiler can see what type you mean without explicitly saying it. So let's say if I have a function, right? I have this function, and I want to call f. I cannot say or I cannot write this. I have to explicitly state what type you want f, the t to be. So in this case, int, for example. That's because the compiler has no way of knowing what type you mean, because it is not able to deduce it. However, if we use this, right, then the compiler is able to deduce it, because it can see that we are passing an integer here. So the compiler is able to deduce t. So now it's going to create an instance of f with int here. So yeah, that's the first rule. And the second rule is it has to be a template class. Let's just say template. It has to be a template, right? And the third one is when you write when t is part of your function parameter, it has to contain two references. So has to contain two references. So that becomes t_ref_ref. And this is maybe a little bit confusing. This does not mean an R-value reference, right? So if I write this t value, then this function parameter, or this function parameter is a universal reference. However, this SD string ref is not, because yeah, that's basically just how C++ works. This means, like, if you explicitly state the type, in this case SD string, then that means you accept only R-value references in this function, right? So we cannot call SD string. Oh wait. So yeah, in this function, if I would comment away this, then you cannot call f like this, right? Because it has to be an R-value reference. And if I will build it, then, well, in this case, of course, it doesn't find a suitable overload. But for this, yeah, this doesn't work because you're passing in a reference and not a R-value reference. So yeah, in the previous video, we saw that you have to move the object. Let me just comment this out, and then it compiles fine, right? But we are not going to talk about R-value references, because that was part one of this video. In this video, I am going to show you universal references, of course. So yeah, a universal reference. What is a universal reference? A universal reference is a well, as the name suggests, it's a universal reference. It may be any kind of reference. So in this case, we are passing an R-value reference to the function f, and that's perfectly fine, because t is a universal reference. So it may be any kind of reference, from being R value reference to L value reference to const L value references, to make it a little bit more confusing. So I'm just going to show you an example. Of course, here this is an R value reference, which is perfectly fine. You can just pass in an R value reference. That's perfectly fine. And we can also call f like this. Of course, you wouldn't see this in production because after moving the string s, it's in the undefined state. It's empty, so it's not safe to do this. But just for illustration purposes, we are going to just pretend that this is fine. So this is an L value reference. And yeah, this is perfectly fine. You can just call f with a reference. So in this case, we're passing an L value reference, and the compiler will create an explicit, or it will create a function for that. And in that case, it will replace t by std string, right? So this function will refer to this function, right? That's perfectly fine. Std string ref is an R value reference, and we are passing in an R value reference. But when we call this function, the compiler is going to create another function for us, namely an std string with one reference, so that is an L value reference. Now we can also create a const std string called const string, and we can call f with const string, and the compiler will obviously again create another function overload for us with std string or const std string. So yeah, this is basically it. And it's you can also pass in arrays, for example. So int r3, for example, and we call r like this. You may expect that the compiler is going to create this function, but it is not int pointer value, because, well, you're implicitly passing a pointer to the array. But the compiler is actually very good in deducing what you're passing here. It is going to create the exact type of what you're passing. So yeah, it's also going to adding the amount of elements within your array. So in this case, it's going to like this, I think, with the syntax, or yes, it's basically I think it's a little confusing syntax, but I think it was this. I think it's this, yeah. So this means an integer array by reference with 3 elements in it. So this function refers to this function. Now, you can also create, and I wouldn't really recommend doing this, but it's also just for illustration purposes, you can also add a volatile int value equals 3, and then we call f with value. Then the compiler is going to create another function, and in that case it is going to be volatile int reference value. That's the exact type of value we're passing here. So yeah, I hope this is will get us a little bit of an idea of how R value, universal references work. So, but things may be a little confusing when, or actually, it gets a little interesting when you refer to t within this function if you have added these 2 references here. So let's say t value, or no, let's not say value, let's say copy equals value. So normally you would think maybe that, oh, okay, you are creating a copy of value, and of course it's the same type as t. But remember what I said, everywhere where t is referenced, it will replace the t. So let's just say if we have if let's just say integer value equals 3, and we call f with std move, or no, let's just say value, then what the compiler is going to do is create a function for us where t is an integer reference. So t will be replaced by integer reference. But remember what I said about everywhere, right? So also within the function. So also here, integer ref copy equals value. But this is not a real copy because you're instantiating a reference. So yeah, this may be a little bit hard concept to grasp, but now that I've typed it fully out, then you perfectly understand it probably. But yeah, so everywhere where you reference t, the exact type of that type will be replaced. So in this case, it's an integer reference. So the compiler sees that you're passing in an integer reference, so it will replace that t by integer reference as well. So and that's what the type traits header, let me just include that, type traits contains, the type traits header contains various structs, and you can use them to ask whether, or you can ask the compiler what type t is. So let's just say we want to know whether t is an integer. All right, so we're gonna say if const expr std is same t and int, right? So if it is the same, then we're gonna print include print, where we're gonna print something out. We're gonna say it's an int, right? Otherwise, std print, it's not an int. Now, it's gonna print it's not an int, and I'm going to show you why that is in a moment. Right, it's not an int. Okay, so let me just clarify what's happening here. So we're going to write out this function for this specific case. So we're passing in an integer by reference, right? So t will be replaced by integer reference. So here I am referring to t as well. So t will be integer reference. So if integer reference and int are the same, then print it's an int. Otherwise, you're gonna print it's not an int. But integer reference and int are not the same, so it's gonna print it's not an int. That's, well, that's no rocket science there. So you may be wondering, okay, but how can I get rid of this reference? How can I get rid of the extraness or extra reference that is being added? Well, you can use, in this case, you can use std remove reference. And what it does is it's going to check whether t is a reference. And if it is a reference, then it's going to remove the reference. Otherwise, it will be t, just t, right? So you don't have to worry about, or you don't have to check whether it's an actual reference and then you can only use remove reference. No, you can use remove reference on t, even if t is not an actual reference. So yeah, std remove reference will remove the reference from t. So now it will print it's an int because now this t is replaced by std remove reference integer reference, and because of how std remove reference is implemented, this reference will be replaced by just a regular type, and then this entire thing will be replaced by int, and then it's gonna print it's an int. So yeah, back to our previous example, if you want to create a valid copy that always works you're gonna say std remove reference t copy equals value. So now we're actually creating a copy of the value being passed. So I have also said about these rules, right? So if I were to remove t, or were to remove this parameter, then you must deduce the type of t, right? So we're just gonna say t copy or t value equals something, just a default initialized value. Then if we create, or if we call f, we have to explicitly state what the type is. So in this case, it's not gonna compile because it's not able to deduce the template parameter for t. So we're gonna pass an integer, so that's will be able to compile. But yeah, you can also, of course, add a reference, but yeah, then it's not gonna compile, of course, because yeah, you're referencing a temporary. You cannot do that. So now I'm gonna show you an example where t is part of or where t is sort of deducible, but not really actually. So let me just create a class, and that's called a vector, and it has a constructor, and it is it has, I don't know, some value, and it's gonna create a copy of that value, and like this, right? So you may be wondering, let's just add this. You may be wondering whether this is a valid universal reference. Well, in this case, it is not, because of rule number 1. T is not deducible. So if we want to create vector, we have to explicitly state what type of vector you want. So in this case, we're going to create a vector int. And even though you have added these two references here, it's not a universal reference. It has become a R value reference, and in this case, that will compile fine. But if I were to add an L value reference, then it's not able to compile because it's gonna complain. It's gonna complain that it cannot bind to a temporary or a reference. Sorry. So all sorts of errors here. Basically, what's it's saying is that you cannot pass a reference type to an R value reference, which is, of course, true. So yeah, this is not going to work. If you want this to work, then you have to create another template so that the t is actually deducible. So you're going to create template class. Well, after t comes u, so let's just name it u. U value. Oops. U value. Now it is able to compile because the compiler is now able to deduce what u is, and yeah, in this case the t is just a regular int, and the u is an integer reference, and a reference, or actually a yeah, there's being copy. There's being a copy being made right here. So if I will build this, then that's perfectly valid, right? In the previous video, we have seen that you can use std move to convert an L value to an R value, and universal. Let's just say like this. So normally, in a regular function, you can use std move to further move the object into another object, right? But we do not know here in this function whether t is a reference or an actual reference, or an R value reference. So what if you wanted to create or wanted to move value if it is possible? Well, let's just say, sure, okay, we're gonna create an if statement. If const expr std is R value reference v, then you can move, because it's an R value reference and you can always safely move from an R value reference. But if it is not an R value reference, let's just say if const expr is L value reference v, right? Then we cannot move safely because it's t ref, right? So you cannot move from you cannot move. Well, of course you can move on a reference, but the user using your function would not expect the reference being moved from, of course. So you can only safely move it if it is an R value reference. So yeah, we can create all this boilerplate, but luckily the standard library has implemented a function called std_forward, which basically does this eventually. So if it is a reference, then it will not move. Otherwise, let's just say if it is safe to move, then move the object. So we're gonna say, okay, we want to move the object if that is possible, but we also have a way. We have to strip away all the types or all the extra value categories from the type. So if the type is const, then we want to strip away const. We just want, let's just say, if the type is const int, then we want int. If the type is, let's just add a reference here. If the type is const or just int ref, then we want int. And if the int is a pointer, then of course we want it also to remain a pointer. So you can use std_dk. It will, I believe, it will get rid of most of the extra type specifiers like const and whatnot, and reference as well, I believe. So most of the times std_dk will be sufficient, but I'm not sure whether this is always the case. But I would just look it up what type stripper, so to speak, to use. So we're going to create a value called std_dkt v, and then we are going to move, or, well, conditionally move value, depending on what value category it has. And by value category, I mean whether it is const or whatever, right? So we're gonna say std_forward t value, and then we're gonna just I don't know, std_print v. So let's just create a std_string value equals I don't know, hello. And then we are going to call universal value and universal std_move value. And then we're gonna just pause the program here. And I'm gonna use the debugger so you can see what's happening. Let's just include IOString. And then things should be compiling. Right. Okay, so we're passing in a reference to a std_string. That's what we're doing because we have added these t_ref and well, it's a template, it's deducible, and it's containing two references. So we're going to step into, and it's going to forward the value, and that's perfectly fine. It's not going to move the value because it's a reference, and you cannot move, well, you can move a reference, but if I would call this function with a reference, then I would be very surprised if a value suddenly is empty after calling this function. So I can expect it to still exist after calling this function, right? So it's going to forward, but that just basically means it's going to create a copy of value, in this case, hello. So as you can see, value is still hello, and v is also still hello. So both values still exist, right? So yeah, we have created a copy essentially of this string, which is which is what you expected, right? So and then it's gonna print the value, and yeah, okay. So now we are moving the value. So the compiler sees, okay, you're moving values, so I don't have to create a copy of it. And we have to firstly actually move the value. So SD forward will only move if the argument is in our value reference. So let's just say it will only move, it is safe to move, right? And you also have to explicitly pass the t of when calling SD forward. So the compiler then actually explicitly passes the type instead of deducing what the type it is. It you're explicitly passing the type here, so the compiler is able to deduce from t instead of the function call, right? So now we are not going to create a copy, but we are moving from value. And you can see that here, value, the function parameter, is now empty, and v, this, is not empty, of course, because we have moved into v. So now we print v, and that's of course gonna print hello. You don't see that here yet, but that doesn't really matter. So yeah, basically we have moved this value into v, and now the function ended, and this value is now also empty because it was contained by v, but now v doesn't exist anymore, of course. But yeah, we have moved value into v because it was safe to do so. And in this case, it was not safe to do that. So SD forward basically told us, hey, I'm dealing with an L value reference here. I'm dealing here with an actual reference. I cannot move an actual reference because that's not what you expect. That's not safe as well. So it just returns the reference and creates a copy of it. And in this scenario, we are moving value, and in that scenario, it is actually moving on this line, making this value empty because we have moved from it. So I hope this made things a little clear about universal references and how to use them. Yes, so if you have any more questions, please let me know, and I'll see you next video. Bye bye.